This lecture deals directly with the ideal gas law. And there you'll see here it says applications of the ideal gas equation. I'm not going to go through those. I highly recommend you do. There will be a few examples we go through, but the applications is much more intricated and many, many more examples. So I highly recommend you going through those sections of the PowerPoints. So, excuse me, with the ideal gas law, first and foremost, we're specifically saying ideal gas because we're talking about gases that are behaving ideally. They are in standard conditions, normal conditions. There is nothing extreme, no extreme pressures or temperatures, etc. And there is a constant involved. So the ideal gas law, much like the combined gas law, is derived from Boyle's, Charles, Avogadro's, and eventually Dalton. We'll get to that in a few minutes. But all these proportionalities that are direct or indirect can be combined into the ideal gas law equation. Hold on, they don't give you the actual, they do. Sorry, I missed it down here. Your ideal gas law, based on the derivation of all the other gas laws, is right here. PV equals nRT. You need to know that. You need to memorize it. You need to know it like you can add 2 plus 2. PV equals nRT, where P is pressure, V is volume, N is number of moles, and the number of moles will either be given or they might give you molarity, from which you can get moles. They might give you grams, from which you can convert moles, but N is moles. R is the ideal gas law constant, which we're going to talk about on the next page, or in the next slide, and then T is temperature. Now, with the ideal gas law constant, you need to memorize this one right here. You need to memorize that one, especially if you're going to be taking Chem 2 as a seated course. Again, it's just one of those constants you do need to memorize. This is going to be the most common one you'll use. You'll note the units are liters.atm per Kelvin.mole. You can use other units which have different numerical values for the ideal gas law constant, but that's only if your problem gives you things like torr or Pascal or cubic meters, etc., joules. In Chem 2 also, this is a very popular one, especially if your teacher prefers to use joules as opposed to liters.atm. So just kind of keep that in mind. It's going to depend on your teacher's preference in your next course. I'm telling you, the very first one is the one we need to focus on the most. So if we're going to talk about how we get this, this ideal gas equation and how different things are involved. When we have gases that are at standard temperature and pressure, this is not the same temperature and pressure. It is standard conditions. By definition, that means 0 degrees Celsius and 1 atm. So at standard temperature and pressure, 0 degrees Celsius and 1 atm, if we're talking about gases that are behaving ideally, we're going to have 1 mole equals 22.4 liters. That's how we're going to get to moles in that particular scenario. Here's an example. It says calculate the volume of a mole of ideal gas at room temperature and 1 atm. Note it says room temperature. That means automatically not STP, not standard temperature and pressure. So we're asked to find the volume of 1 mole, of a mole of ideal gas at room temperature and 1 atm. We were given a pressure, we were given a volume, I'm sorry, not a volume, a temperature and pressure, and we were given a mole. It's assumed you're going to know R, and it's asking for volume. So if it is PV equals nRT, R is understood, everything but volume was given. How do I know it's ideal gas law and not one of the other ones? Because all the other ones had at least 2 of things, 2 pressures, 2 volumes, 2 moles, 2 temperatures, etc. It had 2 of everything. This only has an individual one. R is understood, and it's asking you for the volume. So PV equals nRT. Moles, 1 mole. Temperature, 298.15 Kelvin, that is 25 degrees Celsius converted to Kelvin. P, pressure, 1 atm. I know what I had to convert and what I didn't based on R's units, okay? R's units are going to guide what your other units must be because they need to be able to cancel out. So if we solve PV equals nRT, let me just write this here. Then solving for volume means dividing both sides by P to get V equals nRT over P. And because of my units of R right here, what that means is I have to make sure everything is in moles, Kelvin, atm, and liters. When I do that, what I can see happens is moles cancels, Kelvin cancels, atm cancels, I'm left with liters. So now you just plug and chug. 1 times 0.08206 times 298.15, whole thing divided by 1, 24.5 liters. So other ways that we can utilize ideal gas law if we're not given moles is with the molar mass or molarity and a volume. But we can also derive this equation to find density by using D equals P, fancy capital M, over RT, where fancy capital M is molar mass. So here's an example. It says carbon dioxide is effective in fire extinguishers partly because its density is greater than that of air. So carbon dioxide can smother the flames by depriving them of oxygen. Air has a density of approximately 1.2 grams per liter at room temperature and 1 atm. Calculate the density of carbon dioxide at room temperature and 1 atm. So if carbon has a higher density than air, we should expect to see our answer to be larger than 1.2 grams per liter. So you can very quickly calculate the molar mass of carbon dioxide, which is 44.01 grams per mole, and that's our fancy capital M. And if we use that density equals pressure times molar mass over our ideal gas law constant R times T, we simply just plug and chug. And what we're left with in the end is ATMs are canceling, liters will stay, moles are canceling, Kelvin are canceling, so we're left with grams per liter, okay? In here is when we get into the calculation requirements that have to do with the applied ideal gas law and predicting volumes and all that. This is where I was just kind of telling you that there's lots of problems here and you need to go ahead and just go through them, look over them. They're very detailed, and it's just, again, reusing all the ideal gas law, either the ideal gas law itself or the ideal gas law relationships, which are seen on this slide here, and also understanding this relationship here, okay?